what if you have many sigma-algebras? So let's say assume that you have many sigma-algebras. So we have S1, S1. Then you have another set and a third set. In this case, we define the product S1 times S2 times S3 in the natural way, as we would do. So again, this is of course the set of ordered triples such that each of these SI is in the set SI. What about then the sigma algebra, the product sigma algebra of these things? So what should this be? We have two definitions actually. We could use then define the rectangles from composed of three sets, or we could think the projections. Again, both do the same. So we could say that we define this as the smallest sigma algebra that makes all these projections measurable here. That's the way to do it. Yeah. And so this is the definition of this product of three sigma algebras. And then what if you have infinitely many sigma algebras? So think about having infinitely many with I in some index set, which could be infinite, even uncountably infinite. So then we define the product of SI. Now we use this type of notation, and that product is then again the set of sequences indexed by I, such that SI is in set SI for all I. Then what should be the product sigma algebra? So in that case, we write product I in I, calligraphic SI. Well, we actually use the same definition again. So we say that every projection should be measurable. So this way, that's what we are going to do. In this case, we don't take these infinite rectangles. They might give you a problem. So this is now the better definition to use the projections. And that's the definition of an infinite product of sigma algebras. Do you have questions here?
Is it so that you only consider finite amount of projections at a time when you think of an element in the sigma algebra?
Yes, it is. In this case, it is the case that I'm thinking of, yes, I only look at the one at a time. Each of these should be measurable. And yeah, there can be other sigma algebras as well. Let's look at maybe for an example. So let's take an example. An example is the one, for example, that we look at the product of the real line indexed by t between 0 and 1. So what is this? This is the set of S, t in 0, 1, such that each st is in R now, because we have the same R for every t. So that's the set. So what is this product space actually? It's the space of functions, all functions, which you could think that they are functions mapping from the unit interval to the real line. And again, you could say that t in this notation, t maps to st in this way. Yeah. But let's not worry about this special notation. So we just look, okay, all functions from the unit interval to the real line. And then each of the real line has a sigma algebra. So then we could define the product sigma algebra. So then we could say that product sigma algebra on the real line indexed by this unit interval is then the smallest sigma algebra such that the map is, we could call the map, it's a projection, but we could also call this evaluation map. So it's an evaluation map which evaluates a function. Now the input is a function, and then the output of the map is the value of the function at point t. And we want every evaluation map to be measurable. So that would be the sigma algebra in this case. So, and that would be called the product sigma algebra. On the, you might also call this product if you have this type of product. So then you might write it as just R to the 0, 1 in this way. In practice, you might use some other sigma algebra on this base. You don't always use the product for infinite or uncountably infinite space. Quite often you want to use some other sigma algebra than this one. Let me say maybe quickly, other option. There's more about this in future courses, but let's say equip this space of functions on the real line with some topology. Let's call it T, and then use the sigma algebra, which is the Borel set generated by this open sets here.